So I have a go for the last problem of section 5. I've had a nice dinner, small one though, glass of wine. So I'll just try to solve the last problem and then spend the night reading the next section. So what do we have here? The proof of proposition 9. What can you say about how the second derivative can be expressed in terms of Weierstrass P function itself? So the Weierstrass P function is even and periodic. Never mind that. Differentiating gives that the derivative is odd. And differentiating gain gives that the second derivative is even, as expected. Oh, it didn't say so, but that means that in the expression of the second derivative in terms of the Weierstrass function and its derivative will not occur at all. So it can be expressed in terms of the Weierstrass function, a rational function of the Weierstrass function itself. So we have to check the zeros and poles of this guy. And it's an analytic function, or rather meromorphic function, except the zero at the pole at the lattice point. And we have the expression that I now remember. Differentiating this, which is obviously it's obviously even, of course, so this was not necessary, but it has a pole of order 4 and residue 6. Now, I'll just write that. So that means that we have 4 zeros. Let's denote them. Set 1 to set 4. Now let's look at the function. This guy has a pole of order 4, and this guy has a pole of order 8. I missed that. So then, and the zeros, I don't quite get that. Let's look at the zeros. The zeros, here we have, so they have the same zeros, and then the pole should be the same as well, isn't it? When it's only at naught, there's a pole. Uh-oh. So we need to, but by God, I thought that when the zeros agreed, then well, this has a pole of order, so of order 2. To get the pole of order 4, we need to multiply by the Weierstrass P function of Z. So then it has a pole of order, oh, squared. So then we have a pole of order 2 to the 4th, that 8, and 4th, that 8. But then how about the zeros? I need to look at the proof again. So in the proof it says that Bj is a list of the non-zero poles in the fundamental domain. So how can we evaluate it at the non-zero poles? Oh, that's the Weierstrass function. Of course, that's the poles not being zero, of course. Well, I thought that I had understood it well and was ready to solve it. But in fact, I didn't quite get it. I thought when the non-zero poles and the zeros were accounted for, then the poles at Z equals 0 had to agree. So let's take a little break and then I'll read the proof again and then I believe that I have the answer. So that was very nice. It took no more than 4 minutes. Um, the point is that we don't have to, well, first of all, we shouldn't subtract the set value, but the function value, which is naught. I wonder, what have I done here? Hmm. Well, I'll just write it over. So this should just be 0. It does invisible. Well, we'll have to live with that. And then uh, but there shall only be 2 which we subtract because they come in pairs. Exactly because, now which function is it? It's the double derivative. It's even, and it's so minus the same, -1. So it's Z1 and then minus Z1 and then displaced into the lattice, or maybe only one of them. But so they come in pairs. So actually there are only 2 factors here. And then we don't need this guy because now the poles at 0 agree as they should. So this is a holomorphic function, so we just need to find one value, and that can be the residue at 0. That's unity. Now here it's +6, and here it's unity. So that means that this guy is constantly equal to 6. So that means that, the second derivative equals 6 times So that's my solution. So sorry I missed that detail in the proof, but that's what happens when it's quite a while since I read it. Anyway, that's as much as I can say.